Assalamu alaikum wa rahmatullah. In this video, we are going to explain part 5 of chapter 7, Kinematics 1. In the previous part, we have determined the characteristics of the instantaneous velocity. At the end of this part, we are going to determine the characteristics of the average acceleration and of the instantaneous acceleration vector, and determine the tangential acceleration and the normal acceleration, the physical meanings and expressions. Let's remember the main ideas of the previous part. 1. The average velocity vector is the displacement vector divided by delta t. The instantaneous velocity vector is the derivative of the position vector given by x prime I plus y prime j. The characteristics of v are given by origin, the position of the particle, direction tangent to the trajectory with the direction of motion, and the magnitude is radical vx squared plus vy squared. Consider two vectors, an initial velocity vector and the final velocity vector, where they have the same magnitude. That means the initial speed is equal to final speed. Our aim here is to find their addition and their difference. To find their addition, and using Russell's rule, we have to put the extremity of the final velocity on the origin of the initial velocity, and this vector, which is drawn in green, represents their addition. How do we find the difference? We deal with the difference as if we are finding the addition of the final velocity vector with the opposite of the initial velocity vector. Now, this vector, which is drawn in black, represents their difference and denoted by delta v. Notice that because the initial speed is equal to the final speed, then their difference is 0, but the magnitude of the difference of the velocity vector is different from 0. It is equal to the magnitude of this vector drawn in black. In general, the difference in speed is not equal to the magnitude of the difference in the velocity vectors, unless some specific conditions are satisfied. Acceleration vector part 1. What is the average acceleration vector? Acceleration in general is the rate of change of the velocity vector with respect to time. If in an interval of time delta t, which is equal to the final time minus the initial time, the velocity varies from v initial to v final, then the average acceleration vector is defined by A average is equal to delta v divided by delta t, which is equal to the final velocity minus the initial velocity divided by t final minus t initial. The SI unit of acceleration is meter per second squared. The magnitude of the average acceleration vector is the magnitude of the difference in velocity divided by delta t. What about the instantaneous acceleration vector? The instantaneous acceleration vector A is defined by A is equal to the limit of the average acceleration as delta t tends to 0 plus, which is equal to the limit of delta v divided by delta t, which is equal to the derivative of the velocity vector. Then for the velocity vector v, which is equal to vxi plus vyj, the acceleration vector is written A is equal to v prime, which is vx prime I, plus vy prime j, which is equal to axi plus ayj. What are the characteristics of the instantaneous acceleration vector? We draw the acceleration vector of a particle moving on a curvilinear path in an xy plane. The acceleration vector has two components, ax, which is parallel to the x-axis, and ay, which is parallel to the y-axis. The origin of this vector is the position of the particle. The direction is the resultant vector of ax and ay, or it is the diagonal of the rectangle formed by ax and ay. The magnitude is the magnitude of the vector resulting from ax and ay, which is given by radical ax squared plus ay squared. Application number 1. The position vector of a moving particle is given by OM is equal to 2ti plus 4t squared plus 6t plus 1j. Part 1. Calculate the velocity vector at any time t, that means the instantaneous velocity vector, which is the derivative of the position vector, equal to 2i plus 8t plus 6j. Part 2. Deduce the average acceleration vector between the instants t1 is equal to 0 seconds and t2 is equal to 2 seconds. Here we have to find the instantaneous velocity vector at these two instants, and then we have to Apply the rule, the average acceleration vector is equal to delta v divided by delta t, which is equal to a to j. Part 3. Determine the acceleration vector at an instant t. The acceleration vector is the derivative of the velocity vector, which is equal to a to j. Now we are going to start with acceleration vector part 2. Here we are going to encounter 4 examples. We are going to analyze them and then draw out conclusions about acceleration and velocity. Usually it is not scientifically safe or correct to generalize a result from a special case or example, but for the sake of simplifying the idea, this strategy was used here. Please reproduce this table on a draft and try to fill in it during the presentation of these 4 expected examples. We are going to solve the first 2 examples in this video, and the other 2 will be solved in the next one. We have seen that the acceleration vector is the rate of change of the velocity vector with respect to time. But what varies in a velocity vector? In general, a vector is characterized by its origin, direction, and magnitude. The vector varies if its direction or magnitude varies. Consequently, a velocity vector varies if its magnitude varies or its direction varies. Variation of magnitude of v. When we speak about the variation of the magnitude of the velocity, it means that the direction of the velocity vector does not change, and therefore we deal with a rectilinear motion, and this is what we are going to encounter in example number 1, where we consider a moving object with position vector r is equal to minus t squared plus 10ti. Don't forget to follow up with me and fill in the table while we are solving this example. First, the parametric equations are given by x is equal to minus t squared plus 10t and y is equal to 0. That means the trajectory is the x-axis. The velocity vector is given by vx is equal to minus 2t plus 10 and vy is equal to 0. And the acceleration vector is ax is equal to minus 2 and ay is equal to 0. The magnitude of the acceleration vector is equal to 2 meters per second squared. The minus sign here tells us that the acceleration vector is opposite to the velocity vector. And that means the velocity is decreasing by 2 meters per second every second. In this table, we find the magnitude of the velocity and the acceleration vectors at 2 different instants, 1 and 2 seconds. Now we want to draw these 2 vectors at these 2 instants. Using the scale 1 cm corresponds for 2 meters per second, we draw the velocity vector at time t is equal to 1 second, and using the scale 1 cm corresponds for 1 meter per second squared, we draw the acceleration vector. We do the same thing on the other instant, and now we conclude that the acceleration and the velocity vector are collinear, they have opposite directions, and therefore the nature of motion is uniform decelerated rectilinear motion. Example number 2. We consider a moving object with a position vector r is equal to minus t squared I plus 2t squared j. We will follow the same steps of the previous example. First, we find the trajectory to be a line of equation y is equal to 2x. Second, we find the velocity vector, which has 2 components, vx is equal to 2t and vy is equal to 4t, and the acceleration vector, which also have 2 components, ax is equal to 2 and ay is equal to 4. Now we find the magnitude of the velocity and the acceleration vectors at 2 different instants, which are 1 and 2 seconds. Now we are going to draw the velocity and the acceleration vectors at these 2 instants using the following scale. We note that the velocity vector is the addition of vx and vy vectors. V is tangent to the trajectory, as you can see. The acceleration vector is also the addition of ax and ay, and in this case, the acceleration vector is also tangent to the trajectory. The same steps are used to draw the velocity and the acceleration vector at the other point. Notice that the acceleration and the velocity vectors are collinear because a in this case is still tangent to the trajectory. They have the same direction and the nature of motion is uniform accelerated rectilinear motion. Now you can check the answers for the first 2 examples. The trajectories for both examples was rectilinear. The motion was decelerated in the first example and accelerated in the second example. And for both examples, a and v vectors were collinear, v was variable in magnitude, and the acceleration vector was tangent to the trajectory. Let's now sum up. The average acceleration is given by delta v divided by delta t, which is the final velocity minus the initial velocity divided by t final minus t initial. The acceleration vector is the derivative of the velocity vector, which is vx prime I plus vy prime j, which is equal to axi plus ayj. The characteristics of A are given by origin, position of the particle, direction, resultant vector of ax and ay, and the magnitude is radical ax squared plus ay squared. Thank you for watching this video.